Okay, so in the relativistic treatment of this inelastic collision, let's consider the same inelastic collision that we were looking at before in the non-relativistic treatment, where we have a mass going to the right with velocity v, and in this reference frame a stationary mass and they both have mass m, and they stick together after the collision, and they have a total mass m prime, and they move to the right at v prime. Okay, so now we want to conserve total form momentum. Okay, so the total initial form momentum is equal to, well, the moving particle, remember that that E over C is equal to gamma MC. Okay, so so this is gamma MC, and then the non-moving particle in this reference frame, that we're in its rest frame, and so gamma is equal to 1, beta is equal to 0. It has 0 velocity, so gamma is equal to 1. So this is just equal to MC. The second component, we've aligned it so that everything's along the x-axis. So the second component is actually the relativistic momentum. Okay, remember that the relativistic 3 momentum is shown right there. So everything is along the x-axis, so the y and z components are 0. And so this is equal to, obviously, gamma plus 1 mc gamma mv 0 0. Okay, now for the total form momentum after the collision is just equal to gamma prime big M prime c and gamma prime big M prime v prime. It's still going to be moving along, everything's still going to be moving along the x direction, so the z and the y and z components are 0. Okay, and so here gamma is equal to 1 over square root of 1 minus v squared over c squared, and gamma prime is equal to 1 over square root of 1 minus v prime squared over c squared. Okay. Okay, now if we just equate these two, the initial and final form momenta, okay, then what we get is we get that gamma prime m prime c is equal to the energy component of the initial form momentum, and gamma prime m prime v prime is equal to gamma m v. Okay, and so if we look at these two components and we divide them, so if we divide gamma prime m prime v prime divided by gamma prime m prime c, we see that we get gamma mv over gamma plus 1 mc, and so this is equal to gamma over gamma plus 1 beta. So beta prime is equal to gamma over gamma plus 1 times beta. And we see that since gamma, in any interesting case here, gamma is greater than 1. If gamma was equal to 1, that would mean that the initial particle is at rest and there's no collision. So gamma has to be greater than 1, and so this ratio is actually greater than a half. So this implies that beta prime is greater than beta over 2. Okay, so this departs from the non-relativistic treatment, where we found that v prime is equal to v over 2, or beta prime, which is equivalent to beta prime is equal to beta over 2. Here we don't find that. We find beta prime is greater than beta over 2.